And did you go through the chapter 4 and parts of chapter 5?
My week was a little busy. It went by very quickly,
Okay.
is what I would say. But I couldn't review the chapters because I was busy with other things. Yeah, sorry about that. Maybe from
Yeah,
next
no issues.
next week I'll be able to give
Yeah,
it more time.
sure, sure.
Yeah.
So, like previously, we discussed in last sessions, so many doubts were there. Like, especially I myself was having
Yeah,
so many
yeah,
doubts.
correct.
So, I spent some time on them, and I have created a doc. Let me just share my screen.
Okay. How's your applications going? You said you were applying to PhD, right?
Yeah. So,
Are you
so
applying it
I'm
in India or abroad?
abroad,
Okay,
mostly in
so are
US.
you, oh, US, okay. You're looking for, like, which field are you looking at?
So it's intersection of like two fields. Either like so it's mostly computer vision or
Mm-hmm.
reinforcement learning.
Oh, nice, nice. That's actually something different that I'm hearing after a long time because everywhere I go, people talk about LLMs, LLMs, and I'm like, okay, that's
Yeah, yeah,
not
yeah.
the only field that's there because I am from a computer vision background. Uh, I'm
Okay.
into computer vision and medical imaging specifically. So I am more into yeah, image and the
Oh, great.
video based problems. So then nowadays everyone is like large language models. So it's like, okay, there are other fields too, what's happening in them. So it's good to
Actually,
know.
I'm interested in like intersection of, you can say, NLP and computer vision.
Yeah,
So
yeah, the
that is like
multimodal
yeah,
uh,
yeah, yeah.
models, right?
Architectures like architectures like diffusion and like text
Huh.
to images or text to
Text to
animation.
image. Yeah, yeah, yeah. You showed us some like a graphical thing, right? Computer graphics. You wanted
Yeah,
to
yeah,
give a prompt for it to uh,
yeah.
draw something, right? Like a
Text to 3D.
text to 3D, right? Right. Sorry. Yeah,
Yeah. So
that
given
was actually interesting.
yeah, actually the data for the 3D data available for training is quite less. So the architectures are not there yet. I mean, they're not experimented well.
So then that's a good field to explore, actually.
Yeah, yeah.
Hmm. Okay, I think we have a new member in our group.
Hi, Berto. Hello.
Yeah, you are audible.
Hello, hello, can you hear me?
Yes, yes, yes.
Hi, I just I found a group and recently and saw you guys were going through the what was it called? The Goodfellow deep learning book, right? I am Goodfellow, and so I just
Yes.
and I just thought that um it would be a nice idea to just hop on. I'm a master computer science student, so I've done some, and I specialize in data science, so I've done some deep learning, but I wanted to, have a more maybe
Okay.
proper introduction, not introduction, but walkthrough of deep learning. So thought it would be a good idea to
Great.
hop on.
Yeah, definitely. I mean, we are focusing on more the mathematical aspects of deep learning,
Yeah,
and
yeah, that's the intro, right? The intro part of
yeah,
part one, right, of the book. Going through
yes,
like
yes, yes.
undergrad math, I guess. And where are
Yeah.
you guys right now in the book? What
We
chapter around?
like today we'll be discussing the parts of chapter 4 as well as the intro of chapter 5.
Right, right. Okay, I see. Yeah, because I'm new, so I haven't read the part. So, but I'll be listening, so we'll be fine. I
Yeah,
think.
welcome to the group, and hope you enjoy our sessions and
Yeah, thank
participate
you.
in it.
Yeah.
Yes.
It's
Okay.
yeah.
So, like last time in the last session, we had some doubts in chapter 4. So, I'll be just covering the doubts as fast as we can, and then we can proceed to chapter 5, right? So,
Yeah.
let me just present my screen. Just feel free to interrupt between. Actually, I cannot see my Zoom during presenting for some reason. So, if you have any doubts, feel free to interrupt. Yeah. So, chapter 5 starts with chapter 4 starts with overflow and underflow, and where the author says comments about softmax function. So, what is the author trying to tell here is that if we have like vectors with equal entries, for example, as you can see on the left and right, then on the left you can see the values are so big so that the value of e to the power x will overflow. It's roughly 10 to the power 4342. So, and the limit of numpy is around 10 to the power 308. So this value cannot be computed, so it will overflow. Similarly, in the case when x is very negative, e to the power x is roughly 0. So the denominator of softmax function will be roughly equal to 0, as you can see on the right. So the trick that author has used here is to introduce another variable zi equals to xi minus max of all the xi's. So we can see that uh, when the values are large, I mean, in both the cases, z becomes 0. So uh, the maximum values will be kind of cancelled out and will be computable in the case of overflow. And in case of when denominator is 0, again, uh, we will have at least one value which is exactly 0, z value. So e to the power z will be equal to 1 in that case. So we will ensure that denominator is positive. So this is just a trick that author has mentioned in the start of the chapter. Like, do let me know if you have any doubts. And yeah,
So in a sense, this is kind of normalizing, right? Based it's taking the max and is saying what is the value in terms of the max.
yeah, you can say it as normalizing, I guess, or trying to transform the functions
Right.
into
Yeah.
a smaller dimension. Yes, yes,
Yeah. So sometimes they also do uh, division by max minus min, right? That is called standardization.
Yep. That's right.
No, oh
yeah,
yeah, min max scaling, if
Mm-hmm.
anyone knows scikit-learn. Yeah.
yeah. So if we want to like fix the range of values to some values from minimum to maximum, we can uh, do that, right?
Correct. Yeah.
Yeah. Okay. So, but can anyone tell me why is the softmax of Z1 equals to softmax of X1? Like we have transformed it in another dimension, but will the softmax be the same?
Because it's terminated, well, it will be the same except at the asymptotes, right? So because it's like almost linear in the middle, and then it asymptotes on the 0 and the 1. Y
Okay.
equals 0 and 1. So in the middle, it is almost the same as the incoming value.
Okay. Mm, yeah, actually, yeah, is someone saying?
I feel like, say, we normalize something. At the end of it, we also like remove the normalization, right?
Okay.
Like, I don't know whether I'm speaking right, but say we normalize and we do some process, and like for the result, we try to unnormalize it and get the result, right? So yeah, I think even here, do we do that, or do we just leave it at that? I think I'm
No,
asking a
no,
question over a question.
so let me just, yeah, we leave it as it is. The
Okay.
reason is because max of x will be constant for all i's. Max of xi will be some quantity. Let us say x2. So if x2 is maximum, no matter what I is, this will be x2 always.
Hmm.
So, uh, so we can say that uh, so if z equals to x plus c, where c is constant, we can write softmax of z is nothing but e to the power x1 plus c upon summation e to the power xi plus c. And we know that this plus c can be written as e to the power c into e to the power x1, and will come out and cancel out from the numerator as well as denominator. So this will be exactly equal to softmax of x1.
Okay.
Yeah, that's pretty
Yeah,
clever. Because yeah, it's just a constant, and it's both in the denominator and numerator, so you can just you can factorize them out, and then you can cancel them. Yeah.
yeah. So softmax of z is always equal to softmax of x1, and that is also we are dealing with the overflows and underflows. Okay, okay. So let's proceed to the next doubt we had. Any doubts in the previous question? All right.
No, everything's good.
Yeah. So the next part of the book, uh, the author says that when the condition number of a matrix is large, matrix inversion is sensitive to error in the input. So I've just plotted some extreme cases. Extreme cases. So condition number of a matrix is this ratio of uh, you can write it as uh, I mean, not if all the, it depends on whether the eigenvalues are negative or positive. It's the maximum possible positive ratio of two eigenvalues. So, what is the bound on this condition number? So this has to be at least one, right? This has to be greater than or equal to one, and it can go to infinity also. So when it is equal to one, let us consider one case. For example, matrix says identity matrix. We have eigenvalues 1 and 1. Then we know that output is equals to input, right? So output, what I'm talking about output input here is we have a, we have the equation ax equals to b, and we want to find x. So A is the transformation matrix and B is the input. Now, when A equals to identity matrix, we have X equals to B. So whatever input B is, X will always be equal to that. So a small change in B will produce a small change in X, right? Now, let us see the scenario when condition number is roughly infinity. That is, we can uh, get a case where lambda minimum is 0, one of the eigenvalues is 0, then this ratio we can tend it to infinity, right? So let us consider this matrix where 1 1 1 1, your eigenvalues are 0 and 2, so the condition number is infinity. Now this transformation will be a projection on x equals to y, right? Because whatever you multiply here, x1 x2, the output will be x1 plus x2 and x1 plus x2 in both dimensions, which will lie on the plane x equals to y. So let us just, because this matrix is singular, let us consider an example of similar matrix, which is very similar to this matrix. So instead of 1, we take 1.001 here. And if you calculate the eigenvalues, we get these two eigenvalues. And the condition number is roughly 4001. So if we solve for a dash x equals to b here, where b is, let us say, 2 comma 2, we get x1 and x2, the x vector comes out to be 2 comma 0. But if we just, you know, create a small change in this b, small change, and solve for x, we get x as this quantity, which is very different from the x that we got for 2 comma 2. So here we can see a small change in input b can make a drastic change in output x. So geometrically you can see that uh, I mean, the matrix 1 1 1 1 has determinant 0. So it's technically transforming the data, for example, 2D data onto a single 1D line, here, as you can see on the right.
Mhm.
So if the input B is on this line, we get some value of X. But if it is not on the line or even very close to line, there is no corresponding value to the input. So for any value close to this line, there's no solution for X. But on this line, we have infinite solutions, because if if 1 1 1 1 x1 x2 equals to 2 comma 2, then x1 plus x2 is equals to 2. Now you can just vary x1 and x2 over real numbers and get different solutions, which are like infinite number. So what condition number is doing the matrix is that it's flattening the input in the direction where lambda is like minimum. So as you can see, x1 minus x1 will flatten out and go to the origin, because 1 1 1 1 x1 minus x1 will be 0 0. Whereas if you'll see, x1 point will go out to 2x1 x1, which is kind of extending or expanding in the direction of lambda max eigenvector. So this is the reason why a small change in input can drastically change the output when condition number is high. So this was like one of the doubts in the previous session. Uh, anyone wants to discuss anything? We can proceed to further part. Okay. Okay. So there was also a doubt in the previous session that the author has given this definition of directional derivative and is differentiating with respect to alpha, and using the chain rule, this directional derivative evaluates to be uh, this u transpose gradient of f of x. So how is this happening? So here we can see why are we differentiating with respect to alpha, is because alpha is the distance traveled in the direction where we are trying to estimate f of x. So we have chosen a direction u, and if we move alpha units in that direction from the initial point x, we get f of x plus alpha u. And we want to estimate uh, that how much the function value f of x plus alpha u changes by moving a small distance alpha in direction u. So that is the reason we are differentiating with respect to alpha, not x here. So generally chain rule can be derived from Taylor series. So Taylor series of f of x plus alpha u is something like f of x plus summation this quantity plus higher order values. And this summation quantity is nothing but gradient of f of x dot product with alpha ux. So this is nothing but the chain rule. And if we differentiate this quantity with respect to alpha, then since gradient of f of x and u is independent of alpha, we get this value. So when alpha is like very near to zero, the higher order terms will be very close to zero, and ultimately the limit will be zero. So it will be exactly equal to this one. So in general, chain rule can be derived from Taylor series. Intuition of directional derivative is that gradient is defined as this quantity here. And if you see each term in each dimension, we have considered the maximum deviation in that dimension. So this quantity represents how much f of x changes when we move along x1 direction. So, and that is the maximum possible change that can happen from that point. So this vector is consisting of maximum deviations in multiple dimensions. This is the only reason gradient of f of x represents the maximum change that can happen to f of x from the point x. And when we say we want a directional derivative in some direction u, we can just take a component of this maximum deviation. That is nothing but gradient of f of x dot product with u. So like this is the intuition. Just let me know if you have any doubts. In between, you can interrupt.
Can I ask? So Taylor series was a long time for me, so I need to be reminded. The Taylor series is like a way to approximate, right, the function around a very small distance from the original point, right?
Yes.
The more you deviate from your original point of approximation, the worse the approximation, the Taylor series expansion approximation, whatever you would call it, gets, right?
Yeah.
So in this case, our original. Okay, so wait, the context. What was the context now again? We wanted to show. What did we want to show again? I forgot. Okay,
Like
there.
why is chain rule being used?
So using the chain rule, we can see that derivative of f with respect to alpha. Oh, okay. Evaluates to. Oh, okay. U transpose. The unit vector transpose dot product with a gradient when alpha equals 0. Oh, okay. And then okay, so that's why you use Taylor around the point when alpha equals 0 to approximate the. Oh, okay. And
Yes.
that's
Actually, when alpha is large, then this higher order terms cannot be neglected. So our approximation won't be good in that case because we are approximating them to 0.
Yeah. Wait, so you said when you get far away from the 0, then the higher order terms will be not equal to not approximately 0 anymore.
Actually, these terms have alpha to the power. For example, here it is alpha to the power 1. Higher order terms will have
Yeah.
coefficient alpha
Yeah.
square, alpha cube.
Uh-huh.
And we have neglected this coefficients actually because alpha is close to 0.
Yeah, I see. Yeah. Yeah. So then what you do then when you use tail expansion, let me see the formula. I forgot it was a long time, sorry. Let's see, f of a plus f. Oh, okay, so you're just taking the first derivative, right? The first order derivative, as you said. And then you're multiplying by the distance between the original point and some general points. Something. Yeah, that's okay.
Yeah, so alpha u is basically the difference.
Yeah,
So
the
this is like the
difference.
Taylor series definition of
Yeah.
multiplying with the differences.
And the derivative there is with respect to x now, in not. Oh yeah, that's why it looks like that. Okay, because the alpha u then is just a constant with respect to x, right? So
Yeah, I mean
that's
like
why the derivative looks like, yeah.
x is constant with respect to alpha.
Yeah.
Yeah.
But in the formula right now it says you're taking the derivative of f with respect to xi. So I was talking about that now. It seems to be taking the derivative of f with respect to x.
Yeah. Okay, this one.
Yeah.
This is the chain rule. This is the chain rule version of Taylor series expansion.
Yeah.
This comes because alpha u is nothing but this is nothing but b of x plus alpha u respect to d alpha.
Okay.
I think am I correct or am I getting it wrong? No, sorry. Again. Okay, this
That
is
would
the
be just u,
definition.
right? Yeah.
This is the definition of Taylor series. So like we have defined f of x in terms of uh, derivatives of xi, but then we have differentiated this whole quantity again with respect to alpha.
Yeah.
Yeah. So it's our choice in the Taylor series, like in what variable we want to differentiate.
Yeah.
Yeah. Yes. And like this quantity is like independent of alpha, so it comes out to be constant here later on, like adds up and
I see. Yeah. Okay. Yeah. I'm a bit rusty with these things, so I'm a bit slow. Sorry about that.
yeah, no sure. Yeah, no issues. Uh, yeah, and like feel free to interact. Feel free to interact. Yes. So okay, so we had like one board out in the previous session. That is in this chapter. It is mentioned that okay, anywhere the second partial derivatives are continuous, the differential operators are commutative. That is, this is equal to this. Now I went to the proof online. So I've figured out the easiest proof that is available. It's a bit mathematical. So whenever the partial derivatives are continuous, they commute. So fxy will equal to fyx in that case. So one of the intuitive proof of this is that if we consider these two integrals, that is integration of fyx over this rectangle uh, from a to b and from c to d. This comes out to be this quantity, right? And if we integrate the second integral, which is of fxy, and it comes out to be the same quantity as the above. And since they are equal, we can now analyze the difference of these two quantities. Let us call this function f. And if we integrate this quantity over a rectangle, we can separate fxy here, and we get this minus this. Now we can change the limits here because fyx is continuous in this domain, in this rectangle. Since it is continuous, the integration order won't matter. Now we have seen above that these two quantities are equal, and so this integration comes out to be 0. And this is true for all rectangles that are possible. Now the integration is 0. Now this implies that the function is also 0 because we are considering arbitrary rectangles here. Now if the function, that is fyx minus fxy, if it was not 0, let us assume that there exists some point in the rectangle where the function is greater than 0, then since f is continuous, because f equals to fxy, fyx minus fxy, and both are assumed to be continuous, we can choose a smaller rectangle around this point, x naught, y naught. So we were considering this rectangle. Let us say the integration varies from a to b and from c to d. Oops. If we find a point here for which f is greater than 0, then we can choose a smaller rectangle such that f is greater than 0 for all the points in this rectangle. We can do this because f is continuous. Now, since we can choose such a rectangle, small rectangle, where there is a dash, c dash, b dash, c dash, etc., the integration over this smaller rectangle should be greater than 0 because f is greater than 0 everywhere. But this will contradict the above result that for all rectangles, the integration comes out to be 0. But we found that for the smaller rectangle, integration is greater than 0. So our assumption that the assumption about existence of a point where function is not 0 is itself wrong. So the function must be 0 at all points. So that is the reason. I mean, you can go through this proof if you get time. Like I'll share this PDF. So that is
Proof
the
by
reason
contradiction.
why, yeah, and this is the very reason why we get the Hessian to be symmetric, because the functions are continuous and fxy equals to fy. Anyone wants to discuss anything, or I can just go ahead. Okay. Now, the author says in this line, second derivative in specific direction is given by d transpose ht. Now, why is this the case? Again, you can see Taylor series expansion here. Now, in the Taylor series, we can include the second order terms as well and neglect the higher order terms. Now, if we differentiate with respect to alpha, previously we were getting only this quantity, but including second order term, we also have this quantity. And again, differentiating with respect to alpha, we get this. So this is like the directional second derivative. Okay. And let's proceed to next out. Next out was when u is eigenvector of h, directional second derivative has magnitude equal to corresponding eigenvalue. For other directions, directional second derivative is weighted average of all eigenvalues with weights between 0 and 1. So why is this true? So uh, to check the first thing, it's pretty much straightforward. So if u is eigenvector, u transpose hu, we can replace hu by lambda u since it's an eigenvector of h. Uh, and u is unit vector, so we can replace this by 1. So the directional derivative, second derivative, will come out to be lambda. Now if we have a vector v which is some other direction, we can represent it in terms of the linear combination of uh, eigenvectors of h. And we know that eigenvectors of h are orthonormal with each other because h is symmetric and real. We had this result from the linear algebra chapter that whenever there is a real and symmetric matrix, uh, their eigenvectors would be orthogonal. So we can represent any direction v as linear combination of these all directions. And so we can see that v transpose hv, which is the second order directional derivative, uh, comes out to be this quantity on the right. Now here you can see that ui transpose huj is 0 because they are orthogonal with each other. All right. So, and HUJ, you can write it as lambda UJ, and it will become lambda J UI transpose UJ, and this is 0. So we would only have these terms, Ci square, that is C1 from here, C1 from here, and this quantity, which is again lambda. So we would have directional derivative as a representation of linear combination of all the eigenvalues, and clearly Ci square, the weight, is greater than or equal to 0, and since we are considering v as unit vector, the direction vector, so v dot v is 1, and which simplifies to like Ci square equals to 1, and we have Ci square greater than or equal to 0, which means all of the weights should be less than or equal to 1. So this just proves that for any direction, any given direction, the direction second order derivative is the weighted average of all the eigenvalues of Hessian matrix.
So second order derivative is mainly for determining if the optimum point is a maximum point or a minimum point, right? Or is there
Yeah,
any other benefit?
yeah. There is one more benefit that is discussed in the chapter.
Okay.
So first is that, as you said, like determining what type of extrema we have, whether it's a saddle point or minima or maxima. Uh, Another thing that is mentioned in the last part of the chapter is sometimes gradient descent is not sufficient to detect curvatures of the function. That is where the second order derivatives can be used. We'll come to that also. Yeah, I have included that doubt also. There's one doubt over that. So let's just proceed. And okay, so why is the author concerned with the sign of G transpose Hg? As you said, in gradient descent, I mean G is the gradient here. So we go in the opposite direction of gradient because we know we have to minimize the function, and since we want to minimize and gradient points to the maximum deviation in the function, we want to go in the opposite direction of gradient. Now from point x, if we go to point x minus epsilon g, then using Taylor series again, we have this expression. We have considered the second order derivative also. So here if you see, GG transpose is greater than or equal to 0, epsilon is greater than 0. So this term is negative, I mean positive, and it's being subtracted from f of x. Now this term, if it is, so mainly this term, if this is less than or equals to 0, then f of x minus epsilon g will be less than or equals to f of x. because we are subtracting a positive quantity from f of x, or non-negative quantity to be precise. And if you observe, if we increase the epsilon, so if we have like epsilon 1, which is greater than epsilon, we can write f of x naught minus epsilon 1g again in terms of this quantity by representing epsilon 1 equals to uh, epsilon naught plus epsilon dash. So what we get is that whenever we increase epsilon, this quantity is always going to decrease. So theoretically, a larger epsilon value is always better than smaller epsilon. But practically, at large epsilon, Taylor series won't work because we neglected higher order terms previously. So this is what was discussed. And when G transpose Hg is greater than 0, then we can differentiate this Taylor series to obtain the critical point. So this is to obtain the optimal step size. Yeah. So yeah. So here we can see that in this case we get this step size, and we know that if G is eigenvector of H, we get this as lambda. So we can prove this thing here, that G transpose H is greater than or equals to this quantity. And we have this inequality here, that this step size is between 1 upon the maximum eigenvalue. It can go up to, depends on the sign of minimum eigenvalue. So in the worst case, that is the slowest possible case where it would take a lot of time to converge. So that would be this case. So the step size is very small. And here we know that lambda max is greater than 0, only because this is greater than 0. Because if lambda max is also less than 0, that is negative, then that would mean that uh, H is negative semi-definite. Like all the eigenvalues are negative. And for negative semi-definite, this won't be true. Okay. So like as we were discussing, how can eigenvalues of Hessian determine type of extrema? So in one dimension, we can see that if whenever f double dash is greater than 0, I mean, given f dash is 0, this is minima, this is maxima, and
Yes, sir.
this is inconclusive. Yeah. Similarly, in n dimensions, if all eigenvalues of H are positive, then U transpose HU is greater than 0 for all U. This is the second order directional derivative. So that means that in all directions, second order derivative is greater than 0. We have a minimum. Similarly, if all eigenvalues are negative, that is h is negative definite, we have a maximum, because in all directions uh, the second order directional derivative is less than 0. Now if we have one eigenvalue which is positive and one is negative of Hessian matrix, then for this direction corresponding to the positive eigenvalue, you would have second order directional derivative greater than 0, because uh, uh, for eigenvectors this comes out to be eigenvalues, and eigenvalue is 0, greater than 0. So in that particular direction uh, we would have a minima. Similarly, in the j direction we would have maxima. So in some direction we have minima, in some other direction we have maxima. So that is the definition of saddle point. So this is the case of saddle point. Now if some of the eigenvalues have same sign, that is either negative or positive, and the rest of eigenvalues are 0, then the test is inconclusive, because whenever the derivative is 0, the eigenvectors uh, correspond the directional derivative corresponding to that direction will be 0. So in that direction it will be inconclusive, and in the all the other directions it will be either strictly positive or strictly negative. So this can come out to be a saddle point or a flat surface, a flat point as well. The next case is when all the lambdas are 0, that is h is equal to 0. When that happens, there is literally no curvature. So by curvature, I'm meaning the values of Hessian matrix, the second order partial derivatives. Those are depicting the curvature of the function. So if all the eigenvalues are 0, there is no curvature and the region is flat. So
Right.
so the directional derivatives will be the same in all directions. They won't change. Then we had a doubt. Uh, if you have any doubts, just interrupt in between. Okay. Let me know if you have any doubts. Okay. So one more doubt we had: why does gradient descent work poorly when Hessian has high condition number? So the book discusses that whenever there is high condition number, uh, the gradient descent can oscillate in this fashion. So why does this happen? So Hessian has high condition number, which means the maximum eigenvalue is far more greater than the minimum eigenvalue, which means the rate of change of directional derivatives varies a lot. So there is difference in curvatures. So here you can see at this point, or I think I've created a diagram. At this point X, if you go towards the down direction, that is in direction of lambda max, the gradient itself is going to change a lot with some after some few iterations. This information is given by Hessian, and gradient descent algorithm does not consider Hessian matrix, the traditional gradient descent algorithm, where the step size is constant. So what can happen is, because there is high curvature here, high curvature in this region, for a given step size X, this point can come here, go back again, come back again, go back again.
Mm-hmm.
Because whenever it comes to this point, again, this is the direction of highest, steepest gradient, and but since the curvature is a lot here, it it can cross the minima and go to the other side.
Yeah. Basically, it won't go down in a straight line, right? So if you think in 2 dimensions and you have like a very high curvature on, say, the X side and low curvature on the Y side, your learning rate, if you have it set high enough for the X side, right, you would expect it to go down faster down the the X-axis. However, because the Y-axis is flatter, it will keep bouncing. So it's like, and therefore, because it's all zigzagging, it's not going to go as fast, right? So that's
Yeah. Yes. So the main reason for zigzagging is that because these points have high curvature, even a small step can take you to the other side, and again that would happen for the next time also.
Right.
So since our gradient descent is not taking into account this curvature quantity, uh, whenever Hessian has high condition number, gradient descent works poorly. Like this is the example that is shown in the book. And I think this contour lines probably are, I think the nearer they are, probably the steeper
Steeper it is. Yeah.
it is. Yeah. Yeah, I was trying to visualize this curve, but it's not quadratic. And I tried implementing this, but for quadratic functions, as we go farther away from origin, this gap will reduce. Not sure, like they have mentioned here it's a quadratic function, but not exactly sure what exact function this is.
Does it
Otherwise,
like
probably
does it look like a
yes,
paraboloid or something because of the what's it
yes,
called? You know how it's
Yeah, it's most likely elliptical paraboloid.
yeah.
But I was just trying to implement this, and I was getting the opposite. I mean, the farther as I go from the origin, this spacing was getting reduced.
Hmm.
Probably I messed up with the definition of its contour lines. I'm not sure. I have to check again. But this is a good example showing that gradient descent fails where there is a difference in curvatures in the function. So, so this is the reason the author discusses Newton's method. In Newton's method, we are not assuming this to be epsilon g as we did. That is epsilon the length in the direction of gradient. We are not assuming that. We can differentiate this quantity and get this value to get the critical point. So how to get this critical point? Again, we can write Taylor series expansion up to the second order terms. Now, we are differentiating with respect to x because we want the critical point of f of x, where that would represent a extrema, either minima, maxima, or a saddle point. So, so we want this derivative with respect to x to be 0, which is the extrema case. Then we get these quantities. You can just go through them, and it's pretty much straightforward. I think we get x star is equals to this. So one thing you can notice here is we are getting the inverse matrix of Hessian. So now here, if f is positive definite quadratic function, now positive definite means it is, and quadratic means it is convex function. So since it is positive, we would have minima, and since it is positive definite, so that means there is no any other minima apart from local minima or
There's
global
only
minima.
one.
There is only one minima. Yeah. Yeah. So this is like a special case. So why Newton's method attracts saddle points? Now Newton's method uh, does not take into account the gradient at a particular point. So it just goes to the nearby extrema. So it can either be saddle point, it can either be uh, minima or maxima. So since in Newton's method we are just getting an extrema, it is recommended to use Newton's method when we are closer to minima. Like we know that eigenvalues of h are positive. So eigenvalues of h are positive means, as we have seen earlier, uh, it is positive definite. So for any direction, U transpose HU is positive. That means it is minima. So this was also one of the routes. Now, coming to constrained optimization. Constrained optimization is also not something different. It's just that instead of dealing with all possible x values, we are just constraining our uh, x values to set S, which is known as feasible points. Now, some of the tricks that we can use here, for example, you can see this. If we want to minimize f of x for x belongs to R square, with x constrained to have exactly unit L square norm, we can instead minimize g of theta equals to this quantity. Now, since we have used cos theta comma sin theta without magnitude, we have assumed it is 1. So that is unit magnitude. So just transforming this problem creatively can also solve the problems directly. But for a general approach to solve problems, we have KKT approach. What KKT is basically doing is if our power set S can be represented as uh, represented with some equality constraints and some inequality constraints, then what we can do is we can try to obtain this quantity, that is f of x plus uh, every equality constraint multiplied by lambda I and every inequality constraint multiplied by some lambda j. Now here, since this is equal to 0, so if and this is less than equals to 0, now if we try to find this quantity, this will be nothing but our original problem of minimizing f of x over x belongs to S. Why is this the case? Because uh, you can see these both are maximum values. So over all possible alpha and lambda, we are trying to get the maximum possible value. Now, if if gi of x is not equals to 0, we can maximize this quantity to infinity. We can maximize lambda gi infinitely. So if gi of x is like -5, we can take lambda to be minus, let us say, some big quantity, so that this quantity gets maximized.
Okay.
So if gi of x is not equals to 0, we can make it arbitrarily large. And if this is greater than 0, then again that would be maximized. So to obtain all such quantities, so to obtain the minimum value of this quantity over all x, we want to minimize this maximum quantity over all x. We have to follow these equality and inequality constraints, because if we don't follow the equality constraint, this can go to infinity. And if we don't follow the inequality constraint, it's worse than following the inequality constraint. So this is better because it will minimize this quantity in the box. So this is a creative representation of handling the equality and inequality constraint by just obtaining the value of this quantity. I think this is it. And here they have discussed that if yeah, we say that the constraint is active if the if this quantity is equals to 0 for some x star, we have found some solution x star, and we say the constraint h of x is active if this is 0 for that value of x, and if it is inactive, then we can simply delete that constraint itself. So we get a minimum value for some point x star, and if the constraint hj of x is inactive, that is, it is less than 0, it is not equal to 0 x star, then if we even remove this constraint from this problem, even then x star will turn out to be local minimum. This is simply because uh, the jth inequality here has not contributed anything to this equation. Since it was less than 0, uh, the maximum value it could have taken was 0. So like that is the reason, if uh, any constraint is not active in the solution, you can just remove that constraint and still get the same solution as the local minimum. Yeah, I think like these are the major things that are discussed. Now the conditions here discussed of KKT are these three. First is that the gradient of Lagrangian is 0. So these are necessary conditions, but not always sufficient for the point to be optimal.
Is this the origin of the generally you say in deep learning you don't really care if your function space is very complex, and if you find a minimum, most likely it is the global minimum, right? Because it's so complex, it's kind of hard to find hard to say for sure, but if you find a minima, it is a global. Is this the argument behind it?
Which argument are you talking about?
So
The
this,
previous one?
yeah, the KKT that you just talked about, right? Where it says, like the the second piece, right, where it says it is less than zero. It is always less than zero, so maximum value can only be zero, right? So you can ignore it, right? So is that
Okay. That is an interesting question. I'm not sure. Uh, no, I'm not sure about this right now.
mhm,
I mean, uh, neglecting a constraint uh, and but still we can just comment about local minima. It's not about global minima because
mm,
global minima is I think difficult to obtain iteratively.
right, right,
Yeah, like mathematically it is fine, but uh, iteratively it is very difficult to go
guarantee,
to
right?
global
Yeah,
minima.
yeah.
Yeah, yeah. But it's definitely an interesting question. I'll try to work on it again. So the necessary conditions for the point to be optimal are that the gradient is zero and gradient of Lagrangian is zero. Constraints of on both x, I mean constraints are satisfied, and inequality exhibit complementary slackness. Complementary slackness is like if this is zero, I mean either of these is zero kind of in the solution. So either the alphas are zero, either or the uh, inequality constraints are active. So like this was about KKT. I mean, the book hasn't much described about KKT here, but in future, like in the chapters, if we come across it, we can go through it
Mm,
again.
right, yeah.
So this is a simple example. Uh, so if f of x is this quantity, um, gradient of f of x is this quantity here. We can get this by uh, just writing this as I think a x minus b transpose into x minus x.
Mm,
So the gradient comes out to be this quantity, and the gradient descent is this algorithm where until the gradient is roughly zero, that is, we have some tolerance here until it's greater than that. We are just reducing our x to x minus epsilon times of gradient. Now we can also solve this by Newton's method. So here, if we add a constraint, let us say x transpose is less than equals to 1, that is, we have to do constraint optimization. Then we can write this constraint as uh, this quantity with kkt multiplier lambda. So we can just obtain this min max value. Now we can substitute to uh, so the the Lagrangian differentiation is, again, this was the differentiation we got earlier, that is of f of x, and 2 lambda x comes from differentiating this one. So if we differentiate it to 0, we get x equals to this. Now this is very similar to the pseudo inverse of A. Like we have seen this in linear algebra chapter. Now here we do not know what is lambda. Like we have to find lambda also. Now to get lambda, we can do gradient descent or gradient ascent. So we know that if we differentiate our Lagrangian with respect to lambda, we get this quantity. Now we wanted originally this quantity to be less than 0. So if this quantity is greater than 0, then we can just increase lambda. So if it is greater than 0, and if we increase lambda, what will happen is this matrix will get increased. Now the diagonal elements of this matrix will get increased, and so the eigenvalues of this entire matrix will get increased. So so the inverse of this would mean that x, the norm of x, will basically decrease. So in a way, we can reduce norm of x by increasing lambda in this case. Yeah. So I think this is it. This is chapter 4. And with this, the author has concluded that the mathematical preliminaries are already done. So if you have any doubts, do let me know. Otherwise, we can just proceed with the machine learning portion.
Yeah, I can share screen then.
Yes.
Yeah. Yes. Share screen. Is the screen visible? I don't see it. I'll try again.
You're not presenting anything.
Yeah, that's now I think I.
Yeah.
Yeah. Okay. Cool.
Yeah. Okay.
So okay. So this is the chapter. This is the chapter, and so basically this is the first section is mostly not mathematical at all, except for a little bit about the linear when we do this linear regression example. And so so basically what is the reason for this chapter, right? So he goes into this. There is an area here where he says deep learning is a type of machine learning, and if you you need some solid understanding of the basic principles of ML to understand deep learning, right? So that's the reason for this chapter, basically. And what it does, and this is all covered till about, this bit on the top, right? He basically introduces what are the things that you're going to learn here. So, what is a learning algorithm, definition, and so forth. And he'll give you an example of a linear regression, which is the only mathy part here. And one distinguishing characteristic of machine learning algorithms versus maybe previous rule-based kind of approaches is that you have training data that you use to find patterns. You have training data that you use to fit the model rather than trying to apply patterns to generalize to the distribution, right? The data distribution. And it basically, I don't think it actually talks about how to set hyperparameters. He just mentions it here. And he defines ML here as a form of applied statistics. Yeah, this one. A form of applied statistics to increase emphasis on the use of computers to statistically estimate complicated functions and decrease emphasis on providing confidence intervals. So more numerical based kind of setups. And then he talks about, this is like more, kind of background material. I don't think he goes very deeply into, at least in the first section, he doesn't. Frequentist versus Bayesian. And then, he also talks about using SGD, so stochastic gradient descent. And he talks about an ML model as a combination of the optimization algorithm, the cost function, the actual model, and the data set. So that's your ML algorithm in total. So, and then he again kind of makes a formal definition of what a learning algorithm is. So there is a definition from Mitchell here. It says a computer program is set to learn from experience E, right? So it's here, experience E, with respect to some class of tasks T and performance measure P. So, and the idea is that, as it is exposed to more data, the experience, right, the performance measured by P improves, right, at the task it is supposed to learn, again, T, right. So you can basically think of learning algorithm as a combination of a task T, performance P, and experience C, and he goes into a little bit of in-depth into that. So when you talk about a task, it's basically the author basically differentiates between the process of learning itself. That is not the task, but learning is our means of attaining the ability to perform the task. So basically, learning. So let's say you're trying to, if the task is something like doing sentiment analysis, right? Then the process of learning from data is not really the task. The task is actually the sentiment analysis that it will do once it learns from the data, right? So that's basically, I think, what it's safe to say. And then he gives you a little idea here. Is a piece of data, like an example, is basically a collection of features, right? So this most of us know, so I don't actually think, So and then he goes into a bunch of types of. This is non-exhaustive. He's basically looking at the popular kinds of tasks that can be there. So classification, everybody knows. You basically take an n-dimensional set of data, like your X has n features, and and then you kind of project it into a space where of a set of discrete K classes, right? So that's what this means. You can also, instead of projecting to a set of discrete K classes, you can project it to a probability distribution, right? So if you do scikit-learn, it's the predict proba function, right? It gives you the probabilities of each of the class instead of the actual, class that, instead of the actual class, it gives you the probabilities of each of those classes, and you can select from there at that point. There is also like a variation of classification where it comes with missing inputs. And here, the idea is that, although you learn based on the training data, you learn a model which depends on all of the inputs. At inference time, you might get like a subset of the inputs, right? Because it might be hard to collect those inputs all the time and so forth. So at that point, so essentially the model has learned like a joint distribution on top of the input variables, the features. But if you give it partial features, you can also generate from it 2 to the power n different classification functions, which are missing one feature each, right? And basically you can then solve the classification task by marginalizing out the missing features. So you basically say that I'm going to ignore the feature and I'm going to just, so not really ignore it. I will aggregate the the prediction of the classifier over all possible values. So you take maybe if your values for this missing feature is 0 to 1, you calculate for 0 0.1, 0 0.2, 0 point whatever, and and then you aggregate and you average on that. So you kind of marginalize out the feature of this thing. Similarly, the next one is regression, where you project your input space, the n features that you have, into one floating point feature, right? So that gives you your regression value. So essentially, it's something like if you want to predict, so maybe expected claim amount, as it says here, right? Prediction of expected claim amount that an insured person will make, used to set insurance premiums, or production of future prices. So the output is basically a floating point value rather than one of k classes, like in classification. And it's a continuous value. Transcription is another variation of that, where you basically take a relatively unstructured interpretation, so maybe like an image or a document, and you transcribe the output into a discrete textual form, which can be analyzed further by NLP kind of models, which take this input as a vector of features. So examples are Google Street View uses deep learning to process address numbers from the picture of the address. Machine translation takes one sequence of symbols and produces another sequence of symbols. So basically, like tokens in one language, 2 tokens in another language, and you can do a variety of things. A lot of parsing examples, right? You can think of as translation as well. So yeah. So it's not put in depth here, but you can do that. Structured output are tasks where the output is like a vector with important relationship between the different elements. So examples of this are like mapping a natural language sentence into a tree that describes its grammatical structure by tagging nodes in the tree. So here the output vector, the elements of the output vector are related to each other rather than being totally independent. So that's hence the name structured output. Then you have anomaly detection, where you're basically, the model learns the data distribution, and then if a data point comes in that is not in that data distribution or outside the bounds of the data distribution, it flags it, right? So one of those examples is like fraud, where you as a person, so the model learns your spending habits, and then if somebody steals your credit card, hopefully like he will do something which is not like you, and the fraud model will actually capture that. And synthesis and sampling is this is like based on the distribution the model has learned, it can find other points which is similar to the not necessarily a real piece of data, right? But it can generate synthetic data from the same distribution. So one possible example is like SMOT, where you can do data augmentation, right? Using SMOT. So if you have a set of values, and you want more data out of that data distribution, you can basically interpolate and find. So that's, but there are other ways, other things here also here. So for example, it says speech synthesis task. We perform a written sentence, provide a written sentence, and ask the program to emit an audio waveform containing a spoken version of that sentence. So one thing here is that it need not be one-to-one. So if you have a written input, the way one audio version, say people have different accents, for example, people have different intonations, so the output can be different, and that can as long as it's within the range of data points that the model knows about, it can produce valid outputs, but from different points in that output space. Imputation of missing value is kind of similar to sampling here. A prediction of the values of the missing functions. Denoising is another example where you have to predict a clean version from the corrupted version. Typically, you would train, if you have a data set of clean things, you can arbitrarily corrupt it and produce outputs. And you train, you reverse the data set, and then you train the model on that, on all the corrupted outputs to predict the clean outputs. Variational autoencoders are one example of that. So you learn the distribution of the what constitutes corruption, and then you are able to turn it around and produce clean data. So in formal terms, you basically predict x from the corrupted version x bar, and basically the conditional probability distribution of x, probability of x given x bar, right? Density estimation or probability mass estimation. This one is basically creating a model, right? It asks to learn a function where it's kind of similar to the previous ones, where you are learning this, the distribution, right? So it learns the structure of the data it has seen. So then it can use it for clustering and other examples. So the next bit is the performance measure, which is basically just a quantitative measure of performance. And this is generally, like it's specific to task, the kind of task that you are going to measure. So for certain tasks, which, popular tasks like classification and regression, these are well-known kind of, you can just blindly pick, right? So for example, accuracy or error rate are good for classification kind of examples. The book says average log probability is good for density estimation, right? So you can basically compare two, the predicted density estimation versus the real density estimation, right? So you can use log probability for that. And it also says that, this is basically a skill, and, predicting the right performance is non-trivial, for a given task. So you need to put in a lot of thought, and that's pretty much all it talks about. And the final thing is experience C, and he talks about how much of the data set are you exposed to, is the model exposed to, right? So you can, so unsupervised learning algorithms experience then all learning algorithms that they're talking about experience the entire data set. But then the unsupervised learning algorithm experiences only the data set, the examples, and the features, right? And from there, they learn useful properties of the structure of the data set. So here he says, in the context of deep learning, we usually want to learn the entire probability distribution, whether explicitly as in density estimation or implicitly, like for synthesis or denoising. We talked about this earlier. And then the other, some other roles like clustering, which can take, you basically, once you learn the data set well enough, you can then partition the data set along specific features. So that creates clusters or groups of features. And then attempting to implicitly learn the probability distribution PX. Okay. Whereas with supervised learning, not only are you exposed to the examples with the features, you're also exposed to target classes that those features must project to, right? So essentially, you are learning the probability distribution of Y, the target classes, given X, the examples, right? Yeah, they're not formally. So one interesting point they're talking about here is that a machine learning algorithm can actually be given an unsupervised task and factor it into a bunch of supervised tasks and vice versa. So here it says that, so it says the chain rule probability states that the joint distribution can be decomposed as, this xi given all its previous x's, right? And so it says we can solve the ostensibly unsupervised problem of modeling px by splitting it into n supervised learning problems. And alternatively, we can go the other way as well. We can learn y given x, probability of y given x, by using traditional unsupervised learning techniques to learn the joint distribution, then inferring it like this. I wasn't very clear about how this is done. I think maybe, yeah. So yeah, but we can drill down into this a little bit more. So then he talks about semi-supervised, where some examples include a supervision target, but others do not. So you kind of infer using what you have. You kind of build a model, and then you compute the confidences of the unlabeled pieces, the predictions of the unlabeled, and then you again run those through. You add the high confidence predictions back into your set of supervised classes, and you create another model, and so on. And iteratively you improve your model in that way. And then he talks about, so we already talked about this, one common way. So we spoke about having an example is a group of features, right? So, but you can also think of the example, n examples as a design matrix, right? So if you have, let's say, an example consisting of n features and m examples, then you can think of it as being a design matrix X of size m by n, right? And so here they give you an example of the iris data set, right? And yeah, the other aspect here is that sometimes the label can be more than just a single number. So you could have like a sequence of tokens as, or sequence of token IDs as your label in case of things like speech recognition system or any sequence learning kind of system. Okay, so there is no rigid taxonomy of data sets or experience. Again, things are kind of fuzzy, but overall you can think of a learning algo as being computed, consisting of a task T, performance measure P, and experience E. It helps to formally define such a model or a learning algorithm. The next bit is basically the linear regression. So the idea here is that we are trying to find a bunch of weights. We are given a set of examples with features, or expressed as a design matrix X. We are given a set of labels, like set of class labels, or in this case regression outputs, like continuous outputs that are Y. And our task is to basically find a set of weights where which can be applied to these the specific features. You can think of this as coefficients that will produce something close to the given values of Y, and that will we will state as Y hat, right? And so this W weight matrix is basically called parameters here. And there are a set of weights that determine how each feature affects the prediction. So so now we have definition of task T, and now we have to find the performance P. So the performance P that they have considered is mean square error, and it's basically the definition of mean square error is the label, the expected value minus the predicted value minus the expected value, or the other way around, square it, and for each of the y's that you have, each of the data points that you have, you sum it over all data points and you divide by the number of data points, right? So that gives you an average squared error between the prediction and the label, right? And which now you can, this error measure, if they are almost equal, then this measure will become close to zero, or become zero if they are identical. And so the idea here is that we just talked about gradient descent and optimization, right? So the idea here is that we want to find is, we want to minimize the MSE over all weights, right? So you can do a partial differential of weights over the MSE. And if the places where that is zero, we have found an extrema, right? So here we are saying that this is the global minima. And so we simply solve for where the gradient is zero. And so this is the equation that we are trying to solve for to get the best values of W, right? Most optimal values of W. And so, you replace the MSE with the formula here, right? And so 5.6 becomes 5.7. And then you take Y train, you already know that Y train is this here, right? So you can replace Y train as the X values that you got with the W, right? And then you expand this, or we have already seen this again. Any square value is the transpose times itself, right? And then you expand it out, and once you expand it out, you will get to see that W, the analytical value of W, is X transpose X inverse X transpose Y, right? And this is all training data, so you can find W in terms of what you have already. You can, so again, intuitively, but usually you don't normally do this. You would use something like a numeric method like gradient descent or Newton's method or whatever. And so here, intuitively, if you look at how the MSE varies with W, right? So you will find that this is like this bowl-shaped thing where you have like the minimum point. And this produces this W in 2 dimensions. This will only have 2 values, right? This produces a line that will go, it will become basically Wx plus B, right? You can also pull the B into another, weight for like a unit value, right? So you'll have basically 2 dimensions here, and you should be able to draw a line which it's a straight line, right? And you will find that the points that are represented along the data points that you were given would form like a cluster around these lines. And yeah, so that's basically it. I think that is all I had. Yeah, unfortunately I did not do anything with 5.2. I will do it for next week. So yeah, questions are...
Yeah, I think we can next week we can proceed with 5.2 and later on chapters, later on sections of this chapter.
Right. Yeah. Yeah, this was pretty fluffy, so probably, yeah.
Actually, I'm trying to make analogies between like real life and this machine learning chapter. Like how can we, for every section, how can we put an example? You just remember. I'm not sure how to come up with those, but I'll try if I get something.
You mean like every of these sections, the examples of machine learning?
Yeah, even the terms, right? Interpretation of these terms like denoising or synthesis.
Oh, okay.
Anomaly. Yeah.
Oh, so how as humans we do it, is it?
Yeah, like something like a simple analogy that can help us remember everything in one go. So
Right.
just trying to do that, but let's see. Uh, it would take some time to build a consistent analogy so that there's a single story to remember everything. But, yeah.
There are different variations, though, right? I mean, ultimately, if you think of, for example, the denoising thing, right? Where is this denoising thing? So denoising is basically like a classification kind of thing. You have, you know, data points, and you have like output examples, and you're trying to predict one from the other.
Okay.
Right. So
So
if you
like,
think, yeah. Sorry, go ahead. Yeah.
no, like, why is it termed like denoising?
Oh, so a lot of times, for example, one of the things that you might get is, you might take pictures in the dark, or something, where the conditions are not right, and or even maybe like, yeah, okay, conditions are not right for some examples, or maybe if you're looking at radar and so forth. So those are signals where there is noise in there, right? And you want to produce a clean one. So if you look at deep learning approaches, typically you would, you would have clean inputs. You would deliberately add noise to it, right, to produce an output. So now you have clean to noisy, right? Then you flip the data set. Then now you have noisy to clean, and you train your model with that. So next time you see a noisy thing, it would learn how to do the clean, predict the clean thing.
Okay.
So essentially, the way in which it does it is basically learns the data distribution of the clean thing given the noisy data set, right? And then
Okay.
it's not necessarily actually giving you the correct, right? It's basically using a statistical kind of a data model, like of data distribution, to project your noisy data into your clean data. So it's projection basically, right? So it's all of these are kinds of projection.
Is this the thing used in stable diffusion also? Like, I'm not
Stable
sure. Like,
diffusion, probably.
Yeah, it
um,
does remind me of the backward process in diffusion models, where you have,
yeah.
you start with noise, right? And then you go backwards, and then you try to denoise the noise to a clean image.
Mhm.
And for at least for DDPM, the noising, what's it called? Wait, 1 second. DDPM.
I think the denoising part itself is like assumed to be behaving like the diffusion processes in physics, right? I'm not sure, but I read it somewhere.
Yeah,
I'm
there
not
are
very sure.
some inspirations. Yeah, exactly, from thermodynamics or something. I'm not a physics student, so I don't know anything about that. But it's something, with equilibrium. Like, I don't know, you start with some distribution, and then you destroy this distribution, right? And then at the end you have a noisy distribution, but somehow that turns into some equilibrium. I don't know. Um, yeah, it's weird, but yeah, the noising part, at least, it's reminds me a lot about the diffusion part, the backward process in diffusion in DDPM. Because you can prove it. Actually, you can prove that
Okay.
to learn the backward process, going from a noisy image, noisy latent, to a clean image, you can prove that you can teach a model, a unit, for instance, to learn the loss function of predicting the clean image given a noisy image. So that's practically, I guess, the noising process, right?
Yeah, yeah.
So yeah, in that sense, it's related to some aspect of diffusion models.
Yes, yes.
But we're talking about, you know, machine learning in this context, so it's a bit different, I guess. But for diffusion is deep learning, right? But I guess
well, I mean, it's the ideas are the same, right?
the idea, yeah, exactly.
Yeah,
So
yeah, like mathematically they would be the same, I guess. But
Right.
let's dive deep into the things, machine learning and deep learning in upcoming sessions as well. Actually, for the next two sessions, I won't be able to volunteer as a presenter, but I
Okay.
will be reading the sections and I'll be attending the sessions.
Yeah, I can do the rest of the machine learning. I don't know if it'll take, definitely I can
Yeah,
try
sure, sure.
finishing off.
how long is
Yeah, sure.
the machine learning? Wait, it's chapter 5, and it's okay. It's about 57 pages. I see.
Yeah.
Pretty hefty.
So yeah. So till next week, how much pages can we target? I think the further sections are mathematical, right? I
Yeah.
guess.
Yeah. There is overfitting, underfitting. You already talked about this to some extent.
Okay.
Then there's cross-validation. No, hyperparameters validation sets. Okay. A lot of it is just wisdom, right? I mean, it's not, there's not like, we can go through it pretty quick, I think.
Yeah, if like that is the case, I mean,
Yeah, shouldn't it like serve as a background, just a background, because the rest is just deep learning, right?
Right.
Onwards from this first part.
yeah. Yes, yes. So there are like 11 sections in uh, chapter 5, and 10 out of them are remaining. So can we do like 5 in the next and 5 in the
Yeah,
next
we
next
can
week?
try that, yeah. So till
So
5.6.
yeah, till 5.6 inclusive.
Yeah,
Uh,
we can try.
so that is like till page number roughly 136.
137. Yeah, 136, 137, yeah.
Yeah. Yes. Okay, great. So yeah, anything else anyone wants to discuss, or that we can conclude in this session? We also have problems. There's a link for a question bank. I can reshare it. The description in this Slack group is not being editable, and there are some number of characters limit. So, but I'll try to repost it again. But you can go through the problems and try to solve them. And if possible, like whenever we have time in sessions, we can go through these problems. And if you have any doubts in reading the sessions, the section of like from 5.1 to 5.6 or any other doubt, you can just post it in that uh, Google Doc.
Can I ask, where are the question banks taken from? Are they taken from the book, like exercises, I guess, or?
So like this book doesn't have much of like stated questions explicitly. So
Oh,
we
right.
are gathering questions. Either we have some like theoretical doubt, which we solve it as a question,
Yeah.
or we find some questions online which are good enough.
I see.
So you can contribute to the Google Doc.
Yeah. Could you also is it possible to pin it in the chat in
Yeah, I
the
can pin it.
Slack chat? Yeah, because I don't see it. I see the Zoom link, but I don't see the question bank.
Yeah, I can pin
Okay,
question
great.
bank. Yes.
Yeah.
Okay, then let's conclude today's session. And that's it. Enjoy your weekend.
All right. See you guys.
Yeah,
All right, thank
same
you.
to you. Bye bye.
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 Okay, bye. Thank you.